All right. Okay, so let me start by thanking Ankit and James for the organization. It's a great pleasure to be here. So, unfortunately, there are only weak probes in what I'm going to tell you about, but hopefully the physics would compensate for the lack of non-equilibrium drives. So the people who are involved, and I'm basically, yeah. So I'd like to acknowledge particularly Livio and Tomasz, who did the experiments, and the theory collaboration with Ivan Morera and Eugene Demner. All right, so basically, I'd like to tell you, follow up on what Angel mentioned, and follow up on the use of van der Waals materials for studying strong correlations. As many of you know, this is a big field, and I'm just going to address a teeny tiny corner of it. But again, as a background, what is really important here, or what really brings the new ability, is the fact that you can actually take monolayers or bilayers of very different materials with very different functionality and put them into a heterostructure. And particularly if you do so when bringing together two layers with a slightly different lattice constant, or if they have the same lattice constant, if you do so by bringing in a small twist angle, then you can actually introduce a moire potential, and that is a superlattice potential that modifies the electronic bands dramatically. So again, this whole started, of course, with twisted bilayer graphene by Pablo Jarillo Herrero and co-workers. What has been sort of interesting, particularly interesting, at least from my perspective in the last few years, is that these ideas have been transferred onto semiconducting moire materials consisting of transition metal dichalcogenides, where there are certain advantages and naturally disadvantages. So basically what is, let's say, what we can say here is that once you consider two massive Dirac materials like transition metal dichalcogenides, there is no magic angle. So in fact, the angle is a tuning parameter for what these moire bands could be. That's one could say that's more difficult to do in practice because you get what you get when you make a structure. But thanks to Shahal Ilani's brilliant sort of developments or invention, that this can really become a tuning parameter at this point. And the applied electric field can be used to tune the moire potential, and the difficulties is that it's very hard to get good ohmic contacts onto these materials. So one really relies predominantly, although not exclusively, on optical spectroscopy. And much has been achieved, and the pioneering work of Feng Wang and Phi and J group in Cornell has to be mentioned. So much has been observed, and most recently, fractional churn insulator states have been reported. So I should also add Xiaodong Xu in that sense. Okay, so the one question, though, is if you sort of go to a simpler case, just a triangular potential in a monolayer, the question, one basic question is, what is the magnetic properties of electrons, of holes in such a system? So is it going to be 120-degree Neal order, or could we hope to see spin liquids or something else? Okay, so that's kind of where the question that I will address. So I will try to show you that at least in the systems that we have with very strong potentials and very strong on-site as well as nearest neighbor interactions, the principal magnetic signature is kinetic magnetism. That is really magnetic properties dictated not by exchange interaction, but by minimizing the kinetic energy concentration. So that's the main message that I want to convey. But I will start out by telling you about how we use optics to infer and to study magnetic properties. So you can think of this as a fancy mochi, but there are important differences. Okay, so again, the semiconductor moire materials are, at least so far, have been based on transition metal dichalcogenides. These are, again, monolayer semiconductors with the direct band gap. and you can actually optically excite them. They support very strongly bound excitons. And there are sort of the optical selection rules, polarization selection rules are tied to the valley in which you generate the optical excitation. And you can see the numbers here tabulated by Scott Kruker's group, and what we will be working on is moly diselenide predominantly, which has 230 milli-electron volt binding energy and a Bohr radius of 1.1 nanometer, measured values. Okay, so the reason why these values, particularly small Bohr radius, is important for us is that the idea for what I'm going to tell you is to see if we can probe the electronic correlations optically. Okay, so and optics in this case means a photon comes in, is converted into an exciton, and this exciton, which is a polarizable object, interacts with the electrons. So in normal situations, like in gallium arsenide, when we have a decent electron density, this exciton ionizes. It doesn't really retain or provide a very good, let's say, spectroscopic, let's say, source. That's actually not always the case, but let's say it is problematic. Here, what is important is that because the exciton is so strongly bound, it retains its character, but and in its wave function and spectra is influenced by the exciton-electron interactions, and that's what we want to use. Okay, so let's first understand what these optical properties are. So to that end, first we consider a very simple structure. We have top and bottom gates and a TMD monolayer moly diselenide sandwich in between, and this is the optical micrograph. So what happens is that if you choose the gate voltages such that the material is free of charges, then as you tune your laser field, or in this case it's white light, across the resonance, across the resonances of the system, there is one prominent resonance, and that's the 1s exciton. And this results in a relatively strong reflection signal from the material. And here, actually, this is relatively modest, so the peak reflection is twice as large as the background. In principle, actually, these materials are atomically thin mirrors at the exciton resonance, so their reflectivity can be 85%. And if you suppress background reflection, this signal could have a magnitude of 40. Okay, so in that sense, doing spectroscopy by looking at excitons is relatively easy. Okay, so the main question is, if you change the gate voltage and now inject, say, electrons into the system, what happens? And what happens is that there's a new resonance appearing at low energy, and the exciton resonance broadens and blue shifts. Okay? So how do we understand this? And the understanding comes if you consider this as a scattering problem. That is, if you consider, let's say, an exciton in K valley and an electron in minus K valley, okay, so and the physics is interesting only if exciton and electron occupy different valleys, then, so basically we consider a scattering state consisting of these guys. Their scattering potential supports a bound state. This is the so-called triune state. It's the analog of H- molecule. The exciton can actually capture and form a bound state with an electron, okay? And this interaction potential is 1 over r to the 4 charge interacting with the polarizable neutral object. Now, what happens is, as the exciton and electron come together, and their separation r is small, they will see the triune state and make virtual transitions to the triune state. And through these transitions, they will hybridize. Okay? So, and just as in any case where we have hybridization between two states, we normally consider two discrete states that hybridize. Here, it's actually a continuum of states hybridizing with the discrete state, so it's important distinction. But nevertheless, the effect is that the higher energy state is pushed up while acquiring some bound state character, and that is the origin of the repulsive interactions. That is a generic scenario that whenever we look at the scattering states of two particles in the presence of a bound state, they will act as if they have, they will have effectively repulsive interactions, even if the potential is attractive. Okay? Whereas, on the other hand, the bound state, which doesn't have any optical oscillator strength, through the hybridization with the scattering state, picks up an exciton character, and it redshifts while picking up an oscillator strength. And that's essentially why we have these two resonances in the system. Now, what will be of interest to us is this, what we refer to as the attractive polaron resonance. And the reason for that is that its strength, and we can show this for low densities exactly, is given by the exciton oscillator strength times this quantity, Fermi momentum, times the size of the molecule squared, and this is directly proportional to the electron density in the opposite valley. So therefore, by measuring the polarization selective strength of this resonance, we can determine what the electron density is in the corresponding or in the opposite valley. So these measurements show how well this works. So this is at an exaggerated field of 14 Tesla. So we look at the response for the two polarizations. You see that the attractive polaron is loud and strong in sigma plus, and it's completely absent in sigma minus. Okay, so and this is the line cut which shows this feature. So it really, in this case, we have polarized all of our electrons in the K prime or minus K valley, which means that we can form attractive polarons in K plus and none in the other. Okay? So this is an extreme scenario. What is more interesting is for finite or even small fields where we will have some attractive polaron intensity in the other valley, that is some electron density. And now we can look at the ratio of these strengths to determine the magnetization of the system in the presence of magnetic field, or in principle also in the absence of magnetic field. So in this way, we have a very sensitive and a direct measurement of the magnetization of electrons. So we want to put this into work. So we consider a moire system. In this case, it's not twisted. At least we did not intend it to be twisted. It's this two materials with different chalcogens have a lattice mismatch of 4%, which results in a moire period of about 8 nanometers. Okay, what is nice in this system is that it has type 1 alignment, so that is both the conduction band minimum or valence and the valence band maximum are both in molybdenite. So it almost acts as a simple semiconductor, but with the added moire potential. Okay, so and the electronic bands are trivial. In principle, at least for AB stacking, one should get churn bands, but nobody has seen this so far, and I don't know why. Okay, so again, this is the structure. So this is a sketch of how the moire flat bands should be. This is a calculation for the conduction band and the valence band DFT calculations from Yang Zhang. And the main message here is that the conduction band has very deep potentials. Depth is about 50, 60 milli-electron volts. Actually, the on-site interaction, this is a conservative number, should be even larger than 100 milli-electron volts. The Wannier orbital size is about 2 nanometers, and this is the regime we're going to consider. We're going to inject electrons and see how the optical spectrum changes. But before that, let's look at without electrons again. And in this case, we do not have just one 1s exciton, but we see 3 of them. These are moire excitons because of the fact that the electronic and hole potentials are different. That means that there's an effective potential for the bound electron hole pairs. It's the center of mass potential that quantizes the center of mass motion and results in these so-called moire exciton states. Okay? Now, as we inject electrons, we see that interesting things happen, and we do not understand everything, actually most of the things. But what we do see is that there is an attractive polaron resonance that is appearing now at a more redshifted transition. And what we can really think about this is that now we have these tightly bound electrons in the system, and we can make optical excitation such that the optical excitation is correlated with these. So if you want, it's a collective excitation of trapped trions is one way of thinking about it. And what we can do is we can tune the filling factor and see what happens. And what you can see already here, which I will come back to, is that the oscillator strength picks up, goes to maximum at nu equals 1, and then disappears as we approach nu equals 2. Nu equals 2 means full filling with both spins of the lowest moire band. Okay, and this is another device, and so these costs at nu equals 2 and 3 are generic signatures of incompressibility in the system. We only see signatures of incompressibility in integer fillings, but other materials show also fractional fillings, and actually most likely if we had more sensitive probes like a sensing layer like they do in Cornell, this would also be seen. Okay, so now a movie about sort of what happens as we increase the magnetic field, and not surprisingly, again, in this case, only up to 4 Tesla, just as in the monolayer case, you see that it is the attractive polar resonance that basically is retained only in one polarization. You see modification of the other resonances, but it's mostly line shifts rather than the oscillator strength shift. So this actually proves that this is an attractive polar resonance, and we can use it to probe the magnetization. Okay, so the first thing is that point I made already. As I increase the filling factor, let's look at the red curve, which is the at zero magnetic field. So the oscillator strength increases linearly up to nu equals 1, and then decreases linearly back to nu equals 2. And the reason is relatively easy to understand. Say at nu equals 1, for example, if you have 1 electron at each site, I can make an optical excitation, form this trion. But if I had the additional electron at nu equals 2, then I cannot form such a trion. This electron is now paired, the band is filled, and I can actually forget about them in my description. So this works really better than we thought it would. But anyway, so now the main point is the magnetization. So as I already told you, I can look at the strength of the attractive polar resonances, take their difference, and divide by the sum to determine the magnetization of the system. And from this magnetization, I can take, as a function of magnetic field, I can take the value or the limit as B goes to 0 and determine spin susceptibility. Okay? So at high temperatures, these are what we obtain for different filling factors. And you see that this theta is the Curie-Weiss temperature. So we see this trend that on the nu larger than 1 side, the so-called doublon side, there is a tendency to have ferromagnetic correlations, which are weakened at nu equals 1, and then become even anti-ferromagnetic, but very weakly for nu less than 1 on the whole doping side. Okay, so now how do we understand this? So as I already sort of advertised early on, so at nu equals 1, we normally expect the system to be dominated, the spin physics is to be dominated by super exchange. But hey, U is so large, T, according to DFT, is 1 millielectron volt. Even if I take these numbers, basically, unless I really go down below 100 millikelvin, I would not be able to see, to reach the regime where I see sizable deviations from paramagnetic response. Now, this is different, though. If I go to a doublon side, nu larger than 1, then I have to take into account possibilities for the system to minimize its energy. Okay, so one possibility is the Nagaoka ferromagnetism, which basically tells us that as we consider the hopping of a doublon, right? So this process of this doublon hopping from this side to that side is going to experience a constructive interference if all the spins are polarized. Okay? So if that is the case, all these paths would interfere constructively and would lead to a minimization of the kinetic energy. And the energy scale associated with this now is the hopping strength, which can be orders of magnitude larger than the super exchange. So that is kind of the idea of kinetic magnetism. Okay? Now, It's actually things are supposed to be more interesting on the hole side because of the fact that we're dealing with the triangular lattice. So in a triangular lattice, the hole hopping is frustrated. And in that case, what was predicted by Herter and Shastri, and more recently by Liang Fu and Eugene, that basically spin polaron formation is going to maximize or minimize, the kinetic energy or maximize the delocalization. That is, every hole will try to attach a flipped spin to it and form a polaron state in order to, in this case, get rid of the destructive interference that would suppress the hole hopping. Okay? So this is exciting, but and this is the DMRG calculations from Eugene and Ivan, which indeed shows that this is the limit of infinite U, on-site repulsion. Indeed, boring at nu equals 1, double on-sites and ferromagnetic and anti-ferromagnetic on the hole doping side. Well, life is different. So basically what we saw as we go to very low powers and the lowest temperatures we can reach, which is about 130 millikelvin, we saw that actually if you look at the magnetization at 0.8 filling or nu equals 1, it's identical. So and basically this spin susceptibility is very well described by essentially a Curie-Weiss temperature that is less than 50 millikelvin, and we don't know the exact number because of our error bars. Okay, things are different though. If you go to nu equals 1.2, then you can see this clear sharp increase of the spin susceptibility indicating ferromagnetic correlations. Not ferromagnetic order, so we're still above the temperature. So the critical temperature, despite this enhancement, despite being proportional to the hopping, still is below the temperatures we can reach. Okay? And this is now the spin susceptibility as a function of the filling factor. So you see that it's basically flat, nearly paramagnetic on the hole doping side all the way up to nu equals 1. And then there's a sharp increase associated with the Nagolka ferromagnetic correlations. And then this dip at 4/3 is very reproducible, and we attribute this to the formation of a generalized Wigner state, which again suppresses the hopping. Okay, so that actually brings us to the question of why do we see one kind of kinetic magnetism and not the other? And this, again, we understood by going back to DMRG, where we introduced, or I shouldn't say we, but Ivan introduced disorder as well as nearest neighbor interactions. And this is now the magnetization curve as a function of the magnetic field. And you can see that in the absence of disorder and nearest neighbor hopping, this is the kinetic anti-ferromagnetism, and this is suppressed because of the fact that both disorder as well as the long-range Coulomb interactions lead to a suppression of kinetic magnetism. And this is not sufficient, of course, to understand the whole story. We also see that actually Coulomb-assisted hopping is helping increase the hopping strength on the doublon side by a factor of 10, and which then explains, at least qualitatively, this behavior that one sees kinetic ferromagnetism on the doublon side. Okay, so that's basically the main result. So I thought that I'd finish by comparing it to a parallel experiment that was carried out by Marcus Greiner's group in a very controlled experiment, right? So this is cold atoms. They can actually control everything other than, but they only have on-site interactions, right? So they can go from square to triangular lattice. And indeed, in their case, they're dominated by the super exchange, which actually is reduced as they move away. And in the triangular lattice, they see this tilted curve, and they attribute this to kinetic antiferromagnetism, even though the effect is prominent. The strongest antiferromagnetic correlations, which they measure with their microscope directly, is at nu equals 1. And this is our result, and you see that their result is fully consistent with theoretical calculations. And this is, in a way, the fun of real condensed matter systems, is that you start out with the model, and you see that that doesn't always behave as you expect, and you have to take into account things like the long-range nature of Coulomb interactions. Okay, so that's the main story. So in line with the topic of this meeting, so I'd like to also say that these material systems can also be interesting for having light-induced metastable states, and I call this not so hidden because it's kind of a trivial effect, which was already studied by many groups. That is, if you take a bilayer, it could be homo or hetero bilayer, separated by HBN, if you excite this system, then basically well above the band gap, one ends up generating excitons that are interlayer. Okay, so electron sits in moly, hole sits in tungsten diselenide. And because of the HBN barrier, there is almost no tunnel coupling between these guys, which means that this will be a very long-lived interlayer exciton. With, in some cases, the estimate of lifetime is on the order of milliseconds. Okay, so these were similar experiments were done by, again, the Cornell group. Okay, so now the interesting question is, one can actually generate this by a laser excitation. And wait, so laser excitation could be picosecond or femtosecond long, doesn't matter. You generate this population, and it can actually condense and retain coherence for very long times. Okay, so this, I don't think this has been demonstrated sort of in a foolproof way, but at least in a disorder-free system, one would expect a 2D quasi-condensate, at least in this interlayer system. And then one can argue or think about whether such a light-induced metastable state can be used to modify electronic properties. Say if you have holes in this layer, or maybe in a third layer, whether the interactions between these dipolar excitons and the holes can be used, for example, to mediate exciton, to realize exciton-mediated superconductivity. So in that sense, maybe in a rather trivial way, there might be connections to the topic of the meeting. So thank you for your attention.